There we go. Okay. All right, so everyone, mini exams are up here. The midterms up here. The most recent mini exam, I have not posted grades yet. I should have those by next time we meet. Okay, a quick look. I did this right before class. This is the grades for the midterm. So highest grade was 100, lowest grade was a 10, I think. And we had 5 A's, 2 B's, 6 C's, 2 D's, 6 not passing. Class average on the test was a 71.6. Standard deviation was 20 points. So I think if we throw out the 10, let's throw out the 10 and see what happens. 74, 16, that's more like it. So yeah, that's what happened. Now I don't remember, because I haven't looked at these since since I graded them before spring break, but there was, I had you throw out, what, 2 or 3 problems? 3, right? There were 13 problems, and I only graded the 10 that you told me to grade. So if there are any discrepancies on the grades, if you have questions about that, please get with me during office hours probably. I'll try after class, but I don't have a whole lot of time. So yeah, okay. Any questions? Yes. Well, I didn't do an analysis like that. It was kind of all over the place, honestly. Yeah, as far as like what people skipped. I do have a key, but it's not something that I will share with the class. So it's more something that if you want to come, you can take a look at it, and yeah.
I just want to see. I just need the answer so I know where I'm going.
Yeah. Well, just come by and I can. Yeah. I responded to your. Yeah. Okay. Okay. All right. And then also I sent out yesterday the next mini exam, which is due actually next Wednesday. So you only have a week and a half with it. By the end of today, we should have covered everything you need to do the mini exam. So here's some copies. Just take a copy, pass them around, please. Those are also provided online, so you don't necessarily need a copy of it, but there it is. All right, let's get going. We have a lot to do today. Remember that the final exam will not cover any material from this first half of the, well, if it was on that exam, that material is in the past now, right? So you can just forget it. I mean, I'm sure you probably already started that process over spring break. Okay. So we are going to resume 11.8. In terms of our schedule, we are going to be slightly behind. We are supposed to have our spring break there in yellow. We're supposed to be starting today double integrals over rectangles. We are still in Lagrange multipliers. The good news is that I'm going to be able to cover double integrals over rectangles probably half a class. And so I think I'll be able to get caught up. Next class we'll be able to knock out most of these 2 sections. It's pretty straightforward in terms of just some formulas, just make sure we get the mechanics of it down. Lagrange, on the other hand, is just We just get bogged down a little bit here. So let's resume Lagrange. The whole idea behind Lagrange was if we had some function of 2 variables or 3 variables, and we wanted to find the maximum and minimum values of that function subject to some constraint, then we have this method, right? And I'm just going to pick up where we left off, all right? We were doing example 6. I had done part A, and so I'm going to pick up now by doing example 6, part B. And if you've somewhat forgotten what we were doing, hopefully as I go through this, you'll kind of remember. All right, so there we go. We have a function of 3 variables, f of x, y, z. And what we'd like to know is what is the biggest value you can get out of this function? What's the largest value and what's the smallest value you can get out if you're only allowed to plug in x, y's, and z's that satisfy this equation? So one way to look at this is that this is the equation of a sphere, right? Sphere of radius 1, centered at the origin. So we're saying if you take all the points on the surface of a sphere and you're only allowed to plug those points into this function, then what's the biggest value you can get out? What's the smallest, right? That's the question. So the way to set this up, we're going to set up several equations. First equation we're going to set up is we need the partial of f with respect to x to be equal to lambda, some constant, times the partial of g with respect to x. And I should point out that this left side of the equation is our g function. That's our first equation. Our second equation is we need the partial of f with respect to y to be equal to some lambda, same lambda, g, partial of g with respect to y. Third equation is we need the partial of f with respect to z to be equal to lambda times the partial of g with respect to z. And then the fourth and final equation that must be satisfied is the actual constraint equation itself, that x squared plus y squared plus z squared equals 1. So we need to figure out an x, we need to figure out any x's, y's, and z's and lambdas that make all 4 of those equations true simultaneously, right, all at the same time. So let's do some partials. So I'm going to first take my partial of f with respect to x, partial of this with respect to x. The y and the z parts are like a constant, so I just get 2x y squared z squared equals lambda. Now I take the partial of g with respect to x. Now, because there's addition between these are constants, those derivatives will go to 0, so I just take derivative of the x squared, which gives me 2x. So that's what I get for the first part. Any questions on that? I know it's been spring break. Get your brains going again, yeah? Now a partial with respect to y, which will look very similar to what we just got, except the x squared term is still, or x squared factor is still x squared. The y squared becomes our 2y, so I brought the 2 to the front. Z squared equals lambda, and then same exact thing happens over here. We're taking derivative of y squared with respect to y, which is just 2y. And then the last one, we'll get 2 again, x squared, y squared, this time z, then equals lambda, and then 2z. That all good? Okay, shoot. Okay, what do we do with all this, right? There's so many different algebra approaches we can take here. So one thing that we should maybe consider here is these look really similar. Look, like 2x y squared z squared looks a lot like 2x squared y z squared, which looks a lot like 2x squared y squared z, right? They're very similar. Like this, if I had x squared here and y squared here and z squared here, then they would all be the same, wouldn't they? So I'm going to do this. I have not done this before in a Lagrange problem. I'm going to make all of these left sides identical. And to do it, I'm going to first suppose that x, y, and z are all not 0. Okay? I'm going to say right now, I'm just looking at the scenario where all the x, y's, and z's are not 0. If that's true, then I can multiply both sides of this equation by x, can't I? And multiply both sides of this equation by y. And multiply both sides of this equation by z. If I do that, then I get this. Equation 1 becomes 2x squared y squared z squared equals lambda times 2x squared. Equation 2 becomes, I'm going to multiply both sides by y here, right? So 2x squared y squared z squared equals lambda times 2y squared. And then finally, the third condition is that, or third result is that 2x squared y squared z squared equals lambda times 2z squared. So I multiplied equation 1, 2, and 3 by x, y, and z respectively. I did that so that I make all these the same, so now I can start setting these equal to one another, can't I? So moving on from this, continuing, I have that means that lambda times 2x squared must equal lambda times 2y squared must equal lambda times 2z squared. All of those have to be the same. Right, so I'm just setting each of these equal to one another. I can also get rid of the 2's, right? Those 2's, I can just divide everything by 2, so I don't really need the 2's here. Let's work with the first group right here. If I look at that, I can say lambda x squared must equal lambda y squared. I'm going to bring everything to one side and factor. So lambda x squared minus lambda y squared must equal 0. I'm going to pull a GCF of lambda. And then I'm going to set each one of these equal to 0, right? Well, you know what? Y'all want to do difference of squares here? It doesn't matter. We can do it either way. Difference of squares. So we have lambda times x plus y times x minus y equals 0. And then setting all of these equal to 0, you should get lambda 0, x is negative y, and x is positive y. That's what would happen if I set each one of these equal to 0. Y'all agree? Sure? Yes, yes. Set that to 0, move the y to the other side. Set that to 0, move the negative y, add y to both sides. Yep. We good? So I have that, using those two, I have those results. But what about using these two? I could go through a similar argument, couldn't I? Now, I'm not going to show all the work for that because it's the exact same thing. I move everything to one side, I factor, difference of squares, right, pull the lambda out. What should the result from this say? Lambda 0 or x is negative z or x is positive z. Y'all follow that? Y'all have a question or no? Y'all have that look on your face like you have a question but you don't want to ask? Oh, y's. Oh, well, yeah. Okay, good. I read your faces correctly then. These are what? Y's. Well, if I'm setting these two equal to each other, yes, right? Because I'm working with this. This should go out here, sorry. This and this, I'm working with y's and z's. These first two together, I'm working with x and y's, right?
But if you set the x and z's
yeah, then you would have the same relationship, exactly. So you could have set the outside ones equal to one another as well. Okay, let's start with, we have a lot of different conditions to look at here, right? Yeah. Lots of things. Do you all agree that if I let x be equal to y, let me look at this one right here. If x is y and z is y, right? Then I can go to my fourth equation and I can replace all my x's with y's and all my z's with y's. And then I can just work that equation out. Let's do that. So for equation 4, I know I'm running out of room here. Equation 4 is x squared plus y squared plus z squared is 1. But if I replace my x with y, I get y squared plus y squared plus y squared equals 1, replacing my z and my x with y. So we get 3y squared equals 1, which means y has to be plus or minus the square root of 1/3. Just divide both sides by 3, take the square root, right? All right.
Square minus.
Well, this, okay, you're saying in here? Yeah, the squareds don't matter right here. I mean, the negatives don't matter because I'm a square. And then also here, do y'all see, we're going to square the x, y, z no matter what. And so it really doesn't matter if I use pluses or minuses on these, right? Because I'm going to square them. Let me write down what I've got so far. I've got this potential x, y, and z. I've got my x and y. My x is y and my z is y, and I found that y is that, right? So I have basically plus or minus root 1/3, and then the x would be the exact same thing and the z would be the exact same thing. So plus or minus root 1/3 plus or minus root 1/3. Something interesting is happening when you let x and y and z be those, right? The question is, do these give you a maximum or a minimum? We don't know yet, right? Is this a max or a min? So the way we can check it is we could take this and plug it into the function and see what we get, right? So what would happen if you took f and you plugged in, let's just do the plus and minus, because again, it doesn't matter because they're all squared. If I plug in those three values, plus or minus that, right? Then that's going to be equal to, just square each one of them, you just get, what, a third, a third, a third multiplied all together. So a third times a third times a third is 1/27. 1/27 is either a maximum or a minimum value. I'm not sure yet. We okay? We're always positive, right? I mean, it always looks like it's positive because they're all squared, right? So if we're going to have a smallest value, it would be 0, wouldn't it? But is it even possible to get 0? We have to check, right? We have to check. So what have we really looked at in this scenario? We've looked at these relationships, right? We looked at this, and we've looked at that. What have we not considered? If lambda is 0, right? We have not considered if lambda is 0. So what if lambda is 0? Let's consider that now, okay? So suppose lambda is 0. Okay, if lambda is 0. Now, also remember, we're working under I made an assumption in the very beginning. What was the assumption in the very beginning? That x, y, and z were not 0. Remember, because I multiplied the first equation by x, second equation by y, second by z. So we're still working under the assumption that none of the variables are 0. So if lambda is 0, then what can you tell me about this first equation right here? That side's 0, right? Which means that one of these variables would have to be 0, right? You could make the same argument here. If lambda is 0 here, that's 0. And that means one of these variables has to be 0. But I'm already saying that none of them are 0, right? So supposing that lambda equals 0, that forces either x to be equal to 0, or it forces y to be equal to 0, or it forces our z to be equal to 0. But this would be a contradiction to what I assumed from the beginning. So lambda can't be 0. Good? We're not done. We're not done, because this is all under the assumption that none of the variables can be 0. Now I need to actually go look and see what happens when some or one or all of them are 0, right? All right, So now, suppose, how do we want to do this? Suppose x is 0. Suppose x is 0, and y and z are not 0. I'll just do it that way. Suppose x is 0, y and z are not. So I'm saying, what if one of the two variables, right? One of the two variables is 0. Then is this satisfied?
Yes.
Yes? So equation 1 would be true here. I'm just going to put it like this. Equation 1 is true. Okay, x is 0. If x is 0, that kills this, right? But then that forces what? Lambda to be 0 or y to be 0, right? So equation 2 would force either lambda to be 0 or y to be 0, right? But that can't happen. Y can't be 0 because I'm assuming that y is not 0, right? So I have to look at the fact that lambda is 0. So what if lambda is 0? Is this equation still good?
Yeah.
Because x and lambda are both 0, right? So this is still good. Here, if lambda is 0, right, and x is 0, then this is good, yes? How about here? Lambda is 0, x is 0, this is true, right? So this is a possibility here, that lambda is 0 and x is 0, right? Where do I go now?
Solve for x, y, for y and z.
How? I'm saying x is 0, y and z are not, right? So if x is 0, y and z are not, lambda is 0 then, and everything is good, except what equation has not been satisfied? The fourth, right? The fourth equation hasn't been satisfied. So let's go satisfy the fourth equation. Equation 4 becomes, remember, what's 0 here? X, right? So y squared plus z squared must be 1. How many solutions are there to this? Infinitely many solutions. This is a circle, right? This is a circle with a radius of 1. There are an infinite number of answers to this, right?
Yeah.
All of those answers are going to be critical numbers or critical points that we have to look at, right? Right? Every single point that lies on this circle with x being 0 is going to be a point just like this was. That seems like trouble, doesn't it? Except for one fact. If x is 0, what's the value of the function? 0. And it doesn't matter it does not matter now what y's and z's we get here, does it? We can check all the way around the circle, all infinitely many points. What really matters is that at any one of those points, because the x is 0, that's 0. So I know that the original function's value is 0 anywhere on that circle. That make sense, y'all? So that's a fortunate thing for us, because if that wasn't the case, if that wasn't 0, then I couldn't do this quick check. I would have to actually keep analyzing until I could check points, right? So this right here, this has an infinite number of solutions. But x being 0 implies that the original function, right, if you plug in 0 into the original function for x, doesn't matter what y is, doesn't matter what z is, you're going to get 0 out, right? Does not matter. And so it looks like 0 is an important number, right? Just like over here is 1 over 27. We didn't know if that was a max or a min. But now we know that there's a bunch of places where we get 0 out. So it's looking like maybe that's the min and that's the max, right? Okay, we're not done. See, this is what makes these problems so cumbersome, is that you have to know when you've exhausted all your options, right? We have not exhausted everything. All we had done here is said x is 0, y and z isn't. What should I look at next?
Set y to 0.
Y to 0, and then x and z aren't.
Aren't we just going to get a circle x squared, z squared, and then circle?
Exactly, exactly. So this is where mathematicians like to do this. You could say The mathematical term for this is without loss of generality. That's what mathematicians say. Without loss of generality, which means I'm not being too general that I'm actually losing my ability to state what I'm about to state. I can say that, do I need to write without loss? It's on camera, without loss of generality, all right? If y equals 0, and we have x and z not equal to 0, we will get the same result that f of x0 z will be 0, right? For the same exact argument that we just did here. I'm gonna go and I'm gonna let y be 0. All of these will be satisfied. Lambda 0. I'll set this up over here. I'll get an equation with a circle again, and the same thing happens, but it doesn't matter because y is 0. That function is 0 as well. So without loss of generality, that's true. And if z is 0, then y and x are not 0. You're still going to get at the end that f of x, y, 0 will be 0. Are we done? No, what do I need to look at now?
X is equal to 0, but that's just your constraint, I'm assuming.
Well, no, well, x being 0 and these not being 0.
Well, if they could be 0, is the same.
Okay, so we've already looked at if they're all 0, right? Have we looked at if they're all 0? We haven't, no. We just said all of them can't be 0, right? Okay, so we've looked at one of them being 0, and now we should probably look at 2 of them being 0. And then we'll look at 3 of them being 0, right? Yeah, Lagrange is a mess. So now, starting a whole new suppose over, suppose x and y equals 0 and z is not. Well, first of all, is this even possible? Let's see, if x and y are 0, is this true? Yes? Is this true? Yes? Is this true? Only if lambda is 0, right? Only if lambda is 0. Right, if x and y are 0, this side's 0, and we're already saying z can't be 0, right? So that forces lambda to be 0. So if we suppose this, then that means lambda is 0, right? And now all we have to do is satisfy the last equation, which is just going to be, if x and y are 0, all we get is equation 4 is z squared equals 1, right? Because the x and the y are zeroed out. And there's only 2 solutions to that, right? I don't need to check them, though, because for the same reason over here, if any one of our variables is 0, we know the value of the function, don't we? The value of the function is going to be 0. So even though this is good, this implies that the original function with x and y both being 0 and z being who cares, plus or minus 1, we could check it, but it doesn't matter, we're going to get 0 out, right? And without loss of generality, we could do xz and let y not be 0. And we could do yz and let x not be 0, and we get the same result for each of those scenarios, right? Go with me?
Yeah.
I'm not going to do the without loss of generality again, all right? Okay, one more thing to consider. What if they're all 0? It's very difficult to grade these because I have to figure out whether or not you've exhausted all the possibilities, and that can be troublesome, as you might imagine.
Greatest thing would be for us to solve.
Yeah, possibly. What if they're all 0, right? What if x equals y equals z equals 0? Is that possible? The constraint equation number 4 can't be satisfied that way, right? This right here can't be satisfied. So this is not possible, right? Equation 4 becomes 0 equals 1, which isn't true. So I've covered everything, right? In the very beginning, just to recap, this only took me, what, 20, 30? Oh, shit, 30 minutes almost, okay? very beginning, I said, okay, what if they're all not 0? And I came up with some conclusion, right? Got 1 over 27 at the end. What if I said one of them 0? And then we said, okay, we could do that for the other 2. I said, what if 2 of them are 0? And figured out what that would be, right? And then we said, what if all 3 of them are 0? All right, let's move on. Yes?
I guess we kind of exhausted that, again, the same question I had last time. Was how do you know if you have exhausted all the stuff that you want to? Like, what's
If your very first assumption was that they're not all 0, then at some point you have to allow one of them to be 0, and then you also have to allow 2 of them to be 0, and then you have to allow all 3 of them to be 0. So if you make any constraint in the beginning, you have to look at, what the opposite of that constraint would be, right? Pretty much. So, yes?
Do we know what that one looks like? Like that's
No, visually,
4-dimensional. so
we can't visualize it 4-dimensionally. We can only visualize the restriction. The restriction was the sphere, right?
Yeah.
So if you take points on that sphere and plug them into that function, the biggest value you're going to get out is 1 over 27. The smallest you can get out is 0.
I was sitting there trying to imagine that one, and it was not doing right.
Yeah, you can't really see it.
Yes. And then I remembered, oh, it's 4-dimensional. That explains why it's doing such weird shit.
Yeah. All right, this looks similar to a problem from calculus, I think. It's an optimization problem, right? Find the max volume of a rectangular box with no lid if it is to be made from 12 square meters of cardboard. What are the dimensions? So let me draw a picture first, right? I have a rectangular box. And it has no lid on it, right? Something like that. And I have 12 square meters of cardboard to make up this box. Has no lid, right? I can put my hand inside of it. So what I want to do is figure out how to create this, how to build this so I get the maximum volume, right? Maximum volume. So the thing I'm trying to find the highest thing, right? The highest value of is the volume of this box. So I should probably write down what the volume of this box is. The volume of this box is x times y times z if I label this x, this y, and this z, right? We can agree on that? So if I label it that way, x, y, z, then the volume is just x times y times z. And this volume can be looked at as a function of 3 variables. So this is kind of like the f of x has been for us, right? This is the f of x. Now, there's a constraint though, right? The constraint is that I can only use 12 square meters of cardboard. And that means I can only have a total surface